In the case when we have binary data, so observations X are just a sequence of zeros and ones, so some sequence of zeros and ones, then the average across this data set we're going to denote using p hat. P hat is just the sum over observations and 1 over n. And instead of calling it a mean or average, we're going to call it a proportion. So proportion. The reason we call it proportion because p hat is just proportion of ones in the sequence. So in this sum here, we're going to sum all the ones. So we're going to count how many ones is in the sequence, and then we're going to divide by n. So that's the number of ones divided by n, which is the proportion of ones in the observed sequence. And we're going to call it p hat. And also one more fact about binary data, that variance of this data set can be calculated from p hat. So the variance of x is nothing but just the p hat times 1 minus p hat. And if you remember, when we talked about binary distribution, we also talked about formulas for the variance and the mean, and we talked that the variance can be calculated using the mean of the binomial. But variance of x is just the same formula as we've seen before. It's we average square deviations between each observation xi and p hat. And then by doing some algebra and by doing some simplifications, a simple math, which we're not going to do here, but you can simplify this expression to the expression that we had above. Now, once we know the variance, and also we are going to recall that central limit theorem tells us that the p hat itself follows normal distribution, and we assume that this normal distribution is centered at p hat itself, because that's our best guess about where the center is going to be. So that's an estimate of this normal distribution. And the variance of normal distribution for p hat, you remember, it's given by the variance of the data itself divided by n. And so the standard deviation or standard error for the p hat is given by this formula. So this is a standard error of the proportion p hat. So standard error for p hat. So it's just the variance. On the top we have variance of x divided by n, and then to go from variance to standard deviation, we take the square root of that. And then using central limit theorem, we know that p hat follows normal distribution, and using the properties of the normal distribution, we know that 95% confidence interval for p hat is the p hat itself plus minus 196 times the standard error of the p hat. All right, so let's apply this formula. Let's look at the Google example. Google is testing a new search algorithm, and the way that company does those tests is they randomly select users who come to the website or to their search engine, and a control group will be assigned the old search algorithm. So when I search, if I'm in the control group, then the old algorithm will be used to generate the search results, and the other group is getting the search results from the new algorithm. And Google designed the test in such a way that 2,500 people were in each of the groups, and so we have results for 2,500 search queries, and the data is in the table. So in the old algorithm case, algorithm 1, out of the 2,500 queries, 1,755 ended up to be successful. And let's say we measure success by whether a person clicked on one of the search results or didn't click. So if I go to the Google and I type some query and I look at the results, and if I like one of them and click one of them, we consider that the search was successful. and 745 of the search results ended in a failure, means person haven't clicked to any of those results. And we have the same numbers for the second algorithm. For the new algorithm, we have slightly higher success rate here, so 1880 out of 2500. Now the question is whether this difference, so we have 1755 versus 1818, or if we calculate the proportions, we have 1755 divided by 2500, so that's the proportion for the first algorithm, and this is proportion for the second algorithm. The question is, well, this number is smaller than this number, that's obvious. But the question is, if we are to rerun this experiment, and we're gonna do it once again next week, will this relationship hold? Meaning, will this number be smaller than this number? Okay, so if we are to rerun experiment, the question is, what will happen to this relationship? Will it be small fraction or large fraction? And the reason that the results next week can change is because maybe it's just due to the sampling error that we have this specific outcome, that algorithm 1 performs worse compared to algorithm 2. And if we are to run an experiment, they actually can flip, and algorithm 1 can outperform algorithm 2. So in order for us to give a more definite answer to the question whether algorithm 1 worse than algorithm 2, we have to perform a statistical test. We have to look statistically at these results and account for this sampling error. And the way we're going to do it is by using the central limit theorem and the formulas for the proportions. So if we calculate those proportions, for the algorithm 1, the proportion, this number is 0.702, and the proportion of the second algorithm is 0.727. And now the question is whether the difference between those proportions are actually 0 or potentially can be 0. Okay, so we want to know which algorithm is actually better, and we want to be sure about it in a statistically meaningful way. Okay, so let's calculate the confidence intervals for both of the algorithms. So we take our p hat and we do plus minus 196, and this is just our p hat 1 minus p hat here, divided by n, and then the square root of all of that to calculate the standard deviation. We do the same for the second algorithm, so this is p hat for the second algorithm. And this is 1 minus p hat for the second algorithm. N is the same. In both groups we had 2,500 participants, and so we get our 95% confidence interval. Okay, and now the question is, what can we say by looking at the confidence interval? So if we look at the first algorithm is 693 and 711, and for the it's for the first algorithm, and for the second algorithm we have 718 and 735. We can see that there is no overlap, so no overlap. In other words, with 95% confidence, we can say that the algorithm 2 is better than algorithm 1. And the difference between the proportion of successful visits is not due to the sampling error. And we're 95% confident if we were to run this experiment once again next week, we will see the same result, that algorithm 2 outperforms algorithm 1. And we, in 95% of the cases, the p hat will end up somewhere in this interval for algorithm 1. So this is algorithm 2. And for algorithm 1, it's going to be somewhere in this interval. Okay, and we can do it in a slightly different way. Instead of comparing confidence intervals for individual algorithms, we can compare the means. So we can just look at the difference of the means. So we can look at p hat 1 minus p hat 2. And the question now is, if we calculate the confidence interval for p1 minus p hat, is 0 inside of the 95% confidence interval for that difference. And if 0 inside, then we say, okay, we're not really sure if difference is 0 or not with 95% confidence. Okay, so what we're gonna do, we're gonna calculate the standard error for the difference now. And again, we assume that the experiments for algorithm 1 experiment and algorithm 2 experiment are completely independent. So remember, the variance is just the sum of the variances. So the standard deviation is sum of the variances and then the square root of it. So that's going to be the variance for the first data set. This is the variance for the second data set. Then we sum them up. We take the square root, which gives us the standard error for the difference of two proportions, and or standard difference for two means. And for the proportions, we know that we can calculate this is the variance of the first sample, this is the variance of the second sample. Then we add up those variances, we take the square root to get this is standard error for the difference in proportions p1 minus p2 hat. Okay, now we need to calculate confidence interval for the difference, and we're going to do it by taking the difference itself plus minus 196 times the standard error for the difference, which is this number for the proportions. And if it's not proportion data set, if it's just any data set, then we're going to use x bar rather than p hats. And let's apply this formula to the Google example. So we're going to calculate the standard error for the difference in the proportion. So it happens to be 0.0128. And then we take the difference between the proportions. So that's the proportion 1 minus proportion 2. And this is the standard error for the proportion 1 hat minus proportion 2 hats for the difference in the two proportions. And what we get actually, we get this minus 0.05. And actually, I put 0, 0 here because the number is small, but it's on the left of the 0. So it's so 0 is actually does not happen to be part of this interval. So 0 is outside. So meaning that we are 95% confident that difference is meaningful, meaning that it is indeed different from the 0.